Hello everyone. This program is an introduction to my AutoCAD Blackboard. This online course is free and open to the general public. In this course you can study and learn at your own pace. The course's primary purpose is to assist young engineering students in acquiring the skills necessary to succeed in an engineering career. AutoCAD is an important program that they will be required to master if they aspire to becoming electromechanical, architectural, or civil engineers. The course is also geared to those persons of any age who might be seeking a career change. There are many people who become so engrossed by the program that they studied and learned AutoCAD and became drafters, technicians, designers, and engineers. Welcome to the AutoCAD Blackboard. My name is George Ash. I created this AutoCAD course on CourseSites.com for your benefit. There is no charge for anything you might want to download from this site. To get to my AutoCAD Blackboard, you will have to type the URL https://ashg.coursesites.com. That will take you to this Course Sites page. In the My Courses section, you have to click on Introduction to AutoCAD. When you get to the Introduction to AutoCAD page, click the Browse as a Guest button. After you have signed in and reached the site, the first thing that you will see is a 3D cube in wireframe revolving around the Y-axis. Immediately below the revolving cube, I placed a message for all students. I mention the fact that I have taught AutoCAD in the classroom, hybrid, and online for more than 10 years at the Wentworth Institute of Technology in Boston, Massachusetts. Now I want to mention that prior to coming to Wentworth, I taught AutoCAD at the Computer Ed Business Institute of Boston for 5 years, and that I was a practicing mechanical design engineer for more than 20 years before teaching at the college level. Also in this message, I show a URL where I conduct Adobe Connect meetings or webinars online. I use the webinar to answer student questions and help them if they are having difficulties. To conclude this introduction to my AutoCAD Blackboard, I'm going to show a partial recording on solid modeling which I presented to a group representing the local chapter of the Society of Mechanical Engineers. If you are interested in other engineering disciplines, you will have to view the Blackboard course. Students' solid model assemblies. Here are a couple of solid model assemblies created by some of my students. The detailed drawings from which these models were made are from the technical drawing book by Giesecke and others. Students' mechanical solid parts. These solid model parts were also made by my students here at Wentworth. Many of the students have had little or no experience with any kind of a CAD program before coming here. Many of them show enthusiasm and seem to have fun learning AutoCAD, especially when they are taught how to make solid models during the first week of the course. However, in order to make drawings both 2D and 3D, a student eventually has to learn basic concepts. He has to learn about layers, for every object has to have a layer. With layers you control color, visibility, and whether the layers are on, off, or frozen. Blocks are a useful tool also. Blocks are just groups of objects. A sample block might be a table or a chair. You can save that block outside the drawing file with its own .dwg designation. Blocks can then be inserted into any drawing as often as desired. Scale factor too is very important. You might want to draw a football field and need a scale of 1 to 100, or a map and need a scale of 1 to 500. You might draw something like a laptop or a piece of furniture, and your scale might be 1 to 1 or 1/4. You might want to specify on a drawing different units such as decimal, fractional, or architectural units. Hopefully by the end of my course, the freshman students have learned all that and more. Extruding objects. The extrude command is the basic tool used to create 3D solids. Extrude creates solids from closed objects such as polygons, closed splines, rectangles, circles, ellipses, and regions. When used for extrusion, these objects are called profiles. You can extrude a profile in either a positive or negative direction. Extrusions can have either a positive or negative taper and can be extruded along a straight or curved path. This video clip will show the extrusions of various objects I selected, all in red: a closed spline, a closed polyline, a donut, an ellipse, and a region. I typed 1.5 to specify the height of the extrusion and pressed Enter to accept the default value of 0 for the taper angle. The selected profiles are extruded 1.5 units straight up. Negative extrusion, 0 taper. Next, I repeated the extrude command and picked the blue polygon and blue circle. I typed -2 to specify an extrusion height of -2 units and accepted the default 0 taper angle. You will notice that these objects were extruded in a negative or down direction. Extrusion positive taper. At the top of the screen I drew a magenta colored polygon and typed 1 to specify an extrusion height of 1 unit and 10 to specify a taper angle of 10 degrees. You can see that the taper on the object is clearly visible. Extrusion negative taper. The green circle in the lower left corner will be extruded to a height of 0.5 and given a taper angle of -12 degrees. Notice that the taper angle is going outward. Extrusion perpendicular to a plane. In this last example, a black tilted rectangle is shown. It was extruded to a height of 2 units. You will note that the extrusion is perpendicular to the plane of the profile. Extruding along a path. Profiles can be extruded along a path to create solids of varying forms. First, I extruded the red profile on the right After extrude was entered, I selected P to indicate I want to extrude along that path and pick anywhere on the red polyline. Notice that the profile was extruded along the path. I entered the extrude command again, pick the green circle, type P and pick the green extrusion path. The path used here was a spline curve. Finally, I pressed the space bar to restart the extrude command, picked the blue ellipse and its path and pressed enter. You will note that an extrusion path can be at any distance from the profile to be extruded. Tutorial 18 demonstrates a practical application for extruding along a path. The example shows how to create a handle for a coffee cup by extruding an ellipse along a polyline. It's a good idea to create the extrusion some distance away from the object. Upon completing an extrusion, it can be moved to its proper location later, as shown. Occasionally, I ask students to plot in model space because there's a lot to learn about AutoCAD when doing so. The largest drawing being shown is the assembly drawing. It is shown in the upper left corner and should be plotted at 1/2 scale in order to fit properly on a B-size paper, that is 11 by 17. The standard B-size format is 11 by 17, and if the format is inserted at full size 1:1, the drawing would appear to be too large to fit on the format, as is shown. As a consequence, the B-size format has to be inserted at twice its size in order for the drawing to fit properly. It is necessary to scale the format to double its size. Now the drawing can be properly plotted. On the other hand, if the Geneva drive wheel that I'm showing now is to be plotted at full scale or 1:1, and a B-size format is inserted, the drawing is not too large but fits properly. Here there is no need to scale the format. If, however, we want all the drawings to be on B-size paper, that is 11 by 17, and many companies do, and the same format is inserted for the cam bushing, then obviously the drawing is too small for 11 by 17 or that size of paper. It then becomes necessary to scale down the format to 1/4 of its size so that when the drawing is plotted at a scale of 1:4, the drawing will appear correctly. As it is now shown. Regardless of the scale of a printed drawing, when drawings are printed in either model or paper space, they have to be consistent. All companies want dimension, text, and text height to be standard sizes. Out of necessity, there has to be changes to the variables of dim scale and LT scale, I call it light scale. Remember that dim scale sets the overall scale factor applied to dimensioning variables that specify sizes, distances, or offsets, and light scale is used to change the scale factor of line types for all objects in a drawing. Finally, when a drawing has to be plotted at 1/2 scale, it would require a dim scale of 2, whereas a drawing to be plotted at full scale, 1:1, only requires a dim scale of 1, which is the default. However, plotting at 1/4 scale would require a dim scale of 4, and so on. Even though drawing and printing in model space is good, printing in paper space is better. When you begin designing a layout in paper space to plot, you go through the following procedures. You create a model drawing, configure a plotting device. You activate or create a layout, and specify layout page settings such as plotting device, paper size, etc. You insert a title block create floating viewports and position them in the layout. You set the view scale of the floating viewports and finally plot the layout. That's a lot of work, but the result is worth it. Paper space is a representation of an actual sheet of paper, and floating viewports are windows that frame views of a drawing. In this floor plan, I switched the layout I want to get into paper space, and I want to create two viewports before printing the drawing. By using grips, I made the existing viewport smaller. I've drawn a circle in the upper left corner. By clicking View Viewports Object, a circular viewport is created. Now I double-click inside the viewport to get back into model space. Then I can pan and set a new scale for the circular viewport so as to enlarge a particular view. Also, I use the MView command to create a rectangular viewport for an enlarged view of a different part of the floor plan. Note that up to 15 viewports can be created on one layout if desired. Boolean operations. You can use the Boolean operations to create complex solid models. The following tutorials are excerpts from my tutorials online at youtube.com. These tutorials show how to use the operations of union, subtract, and intersect. The union command defines a new solid that consists of the common and uncommon volume between two or more solids. When using the subtract command, two sets of solids are selected, and a single solid will be created based on the subtraction of one solid from the other. The intersect command defines a new solid based on the common volume between selected solids, and all other material is discarded. Tutorial 1. In this drawing, I'll create a solid model of the object and place it in the upper right corner of the drawing. I'm using a split screen as a convenience. I use the rectangle command, copy the two rectangles, and move them to the upper right. Extrude the two rectangles to a height of 1 unit each. I'll use the endpoint O-snap, grab the small red box and move it on top of the larger box. Use the union command to join both boxes together, render the object, and the solid is complete. Then I can click on the Layout 1 button, move into paper space, and create a small rectangular viewport for the new model. When the drawing is ready for printing, it will contain orthographic views and also any desired view of the 3D model. Tutorial 2 is another simple detailed drawing. A solid model of this object will be created and placed in the upper right corner of the drawing. I'll use a polyline and trace over the perimeter of the top view. And when that is completed, I'll move the tracing to the right and go into the southeast isometric view. Now the object will be extruded to a height of 2 units. And then I'll use the 3D rotate tool and rotate the object 90 degrees clockwise. After rendering, the solid is complete, and I can click on the Layout 1 button, move into paper space, create a small rectangular viewport for the new solid. This drawing consists of 3 solids which have not been joined together. I use the rectangular command and trace over 3 squares in the top view and move them to the upper right. Go to southeast isometric and extrude all squares to a height of 1 unit. Change the colors of the boxes and move them to the desired location. When that is done, I'll render the objects and the solids will be complete, but they will not be joined. At this point, I can click on the Layout 1 button and move into paper space, create a small rectangular viewport for the new solid. I know that these simple objects are easy to understand and create in 2D and 3D. Nevertheless, I have to remember that most of my students are freshmen and have never had experience with any kind of a CAD program. These projects were designed to be simple so that new students would develop confidence and not be easily discouraged. In this project, a solid model of the object will be placed in the upper right corner of the drawing. Using the rectangle command, I'll trace the three rectangles in the top view. I'll go into southeast isometric view and extrude them. Using the O-snap command, move all the boxes to the desired location. With the union command, join all the solids together to form a new object. Render the object and the solid is complete. Then click on the Layout 1 button, move into paper space, and create a small viewport for the new solid. In this tutorial, another solid model will be created. The Boolean subtract operation is important here. Use a polyline and trace the perimeter of the front view and move it to the upper right. Use a polyline to trace the small right triangle. Move into the southeast isometric view. Extrude the four-sided polygon to a height of 0.75. Extrude the triangle to a height of 0.25. Select both solids and rotate them 90 degrees counterclockwise using 3D Rotate tool. Use the O-snap set to midpoint and move the triangular solid inside the larger solid. Subtract the triangular solid and render the object, and the solid will be complete. And once again, move into paper space and then create a small viewport for the new solid. Tutorial 6. This is another easy example of how the Boolean subtract operation can simplify the making of a solid model. I'll use a polyline, trace the perimeter of the large triangle and move it. Then I'll use a polyline again to trace the small triangle. I'll move into the southeast isometric view, and then I'll extrude the large triangle to a height of 1.38 units and extrude the small one to a height of 0.63 units. I can select both solids and rotate them 90 degrees counterclockwise using the 3D Rotate tool. Using O-snap set to endpoint, move the small triangle solid inside the larger one. Subtract the smaller solid, render the object, and the solid is complete. Boolean intersect. The Boolean intersect operation creates composite solids from the intersection of two or more solids. Intersect calculates their common volume and forms a new object. All material outside the overlapped area is discarded. The intersect operation often results in useful and interesting objects. Intersect example 1. Here we have a sphere and a cube. I'll move the sphere from its center to the center of the cube. The two objects appear to overlap each other. Now I'll enter the intersect command and pick the red sphere. The new composite object will be placed on the layer of the first object selected. Now pick the green cube second and press enter. Note that the portions of the sphere that were not part of the volume of the cube have been discarded. In the intersect example 2, we have a sphere and a green cone. I'll move the cone from its bottom center to the center of the sphere. Again, the two objects appear to overlap each other. I'll enter the intersect command and pick the green one. The new composite object is placed on the layer of the first object selected, and so that when I pick the red sphere second and press enter, you'll notice that the portions of the cone that were not part of the volume of the sphere have been discarded. Revolve curves about an axis. In addition to the solid command of extruding, this is another way to create a solid object. You can revolve a closed polyline about an axis. The profile must be closed, and also the axis about which the profile is revolved can be located at any distance from the profile. This is Tutorial 7. My goal here is to put a 3D solid in the upper right corner of the screen. I'll click on the Model button to get back into model space. Then I'll split the screen into two vertical viewports. The viewport on the right will contain only half the profile of the shaft. A profile to be revolved must be closed, so I use the polyline edit command to make a single continuous line in order to revolve this profile. I'll type revolve and select the profile, and then select the upper and lower axes about which to revolve it. The object is rendered and the solid is finished, so I'll click on the Layout button and set up the desired viewports in Paperspace. I'll freeze the viewports layer, and the detailed drawing is ready for plotting. This is Tutorial 20, and we're going to make another solid model. This time, the profile to be revolved will be at a distance from the axis. Also remember that I made one continuous polyline out of it using the polyline edit command. Of course, I could have used the other method by just tracing over the profile with another polyline. Now I'll move into the southeast isometric view. I'll type revolve enter and select the red profile, and specify the axis start point at the upper left end of the center line and use the lower right as the end point, and press enter to accept the default revolution of 360 degrees. Next I'll type extrude enter, select the three holes, extrude the holes to an arbitrary height of 5 units. Now I'll use the 3D rotate command to rotate the 3 cylinders 90 degrees clockwise. I have to move the 3 cylinders forward so that they penetrate the wheel. When I subtract the cylinders from the wheel, the 3 holes will be formed. The solid is completed, so I'll click on the Layout button to get into Paperspace and set up the desired viewports. When the viewports layer is frozen, the detailed drawing is ready to be plotted. Revolving a profile partially about an axis. Remember that the profile to be revolved must be closed, and that the axis can be located at any distance from the profile. I typed revolved and picked the profile and pressed enter. Type O to select the object option. Then you pick the left end of the axis line and type 90 to revolve the profile through 90 degrees. Since a point at the left end of the axis was selected, the profile is revolved above the XY plane. If you type revolve again and pick the lower profile and type O to select the object option, this time pick the right end of the axis line, and you type 90 to revolve the profile through 90 degrees. This time, since a point at the right end of the axis was selected, the profile is revolved below the XY plane. How to fillet solids. After a solid model is drawn, it can be modified by adding fillets to round off edges. In example 1, this box has straight and curved segments. Enter the fillet command, specify a radius of 0.3 and select the top front edge. Pick all the remaining edges, including the curved edge, and you'll notice that the edges that were selected have all been filleted. In the next object, two objects are unioned together. You pick the bottom edge of the cylinder, type 0.25 for the fillet radius and press enter, and a fillet occurs between the cylinder and base. Applying a chamfer between two surfaces, example 1. Apply a chamfer to two adjacent surfaces of a solid. You enter the chamfer command and pick the edge common to top and front faces. Then you'll type 0.8 for the base surface distance and 0.4 for the other surface distance. And then you select the edge separating the top and front surfaces and press enter. And you'll notice that the edge becomes beveled. In example 2, use a copy of the last object. Pick the top edge of the curved corner. If it highlights, press enter. Type 0.3 for the base surface distance and 0.3 for the other surface distance. Since you want to chamfer all the edges on the surface, type L to choose the loop option. Pick one of the edges of the top surface and notice that the entire surface highlights. Press enter to carry out the change. Tutorial 22. In this tutorial, I'm going back to the split screen again so that you can understand better what I'm saying and doing. I'm going to trace over the two rectangles on the top view and move them to the upper right. I copied the holes from the top view to the new red rectangles, used a polyline to trace over the upper part of the right side view and move that copy to the upper right. Use the polyline edit command to make sure the view closed polyline. Moved into southeast isometric view. Extrude the two rectangles, including the holes, to a height of 0.25 and subtract the hole. Then extrude the larger rectangle on the right, including the holes, to a height of 0.34 and subtract the holes. Extrude the remaining part to a height of 0.34 units. Activate the O-snap endpoint and move the small box from the upper right corner to the lower right corner of the large box. Union the two rectangular boxes. Then I'm using the 3D rotate tool I'll select the last part and rotate it clockwise 90 degrees. Again, using the 3D rotate tool, rotate the same part another 90 degrees clockwise. And now I'll move that last part from its lower left-hand corner to the upper left-hand corner of the other part. And with the union command, make all the parts into a single object. When that is done, I'll shade the object and the solid is complete. Then I'll set up the two viewports as desired in Paperspace, freeze the viewports layer, and this drawing will be completed. This is an abstract of tutorial 26. In this drawing, I used a polyline to trace over the top view, subdividing it into two parts. Then I will move those profiles to the upper right, and of course make certain that both are closed polylines. I move into the southeast isometric view and extruded the large profile to a height of 3 units and the smaller to a height of 7.75 units. And with the O-snap set to midpoint, move the parts together and union them. Then I extruded the 4 holes to an arbitrary height of 5 units, entered the align command, selected the 4 cylinders. The align command will rotate and move the cylinders into the main bracket. Then I can subtract the cylinders from the main bracket and the 4 new holes are completed. Shade the solid and the bracket is complete. Click on the Page Setup Manager to modify the layout to accept a B-size paper, then click on Layout 1 button and set up the necessary view. This is tutorial 33. In the right viewport, I'm going to draw 2 concentric circles. And then I'm going to move into the southeast isometric view. I'm going to extrude the larger circle and the smaller circle. And I'll draw a vertical line connecting both ends of the larger diameter circle. Then I'll draw a horizontal line a distance from 1.5 starting at the midpoint of the vertical line. Where the 2 lines intersect, I'll draw 2 concentric circles. And then I'll rotate those 2 circles clockwise using the 3D rotate tool. I'll extrude the circles. Then I'll subtract the larger vertical cylinder from the larger vertical, the smaller cylinder, and press enter. Then I can subtract the 0.6 horizontal cylinder before shading the object. I placed a fillet weld at the seam where the 2 pipes meet. Shade the object, the outlet pipe is completed, and I can move into Paperspace and finish the drawing. The simplest form of a surface in AutoCAD is a 3D face. 3D faces are flat surfaces with 3 or 4 straight edges. The 3D face command is used to create 3D faces. The objective here is to cover the rectangle and the hexagon with a 3D face. First, I'll enter the 3D face command and then click the corners of the rectangle either clockwise or counterclockwise. The rectangle is now covered with a 3D face. To cover the hexagon with a 3D face, I'll have to click on all the corners of the hexagon in either clockwise or counterclockwise direction.
So I'll enter the 3D face command and then just pick all the corners of the hexagon until it's accomplished. If I click on the 3D Hidden Visual Styles icon, the internal lines of the hexagon will disappear. The slice command cuts through a solid based on a defined plane. You can keep both parts of the solid or one part and discard the other. In this example, I show how to use a cutting plane to slice a solid. Here we have a sphere and a cutting plane that was created by the 3D face command. What I'll do is move the 3D face so as to cut through the sphere. Now I'm going to enter the slice command. I'll pick the sphere, then I'll pick then I'll pick the 3-point option and select 3 points on the cutting plane, and the sphere will be sliced in half. In this case, I decided to keep both halves and erased the cutting plane. In this next example, I have a blue sphere and a red line. The red line can be used to define a cutting plane for the slice command. I'll enter the slice command. Then I'll pick the sphere and press enter. Then I typed O to indicate that I want to use the object option. And so I picked the line, and the sphere is sliced. I moved the parts apart and erased the red line. The align command allows you to do a 3D rotation and displacement and scale at the same time. Using this command, you can align one solid model with another one. The first thing I'll have to do is switch to the wireframe mode. And now, with OSNAP set to endpoint, it's a simple matter of simply connecting endpoints. I'll enter the align command and then select the object I want to align. The two models can then be joined together using the union command. If a 3D solid model is not required in a drawing, you can print the drawing in either model space or paper space. Some companies prefer not to use paper space and rely on model space exclusively. I was employed by such a company when I made the drawings that you are now viewing. These drawings include a desk, cabinet, and a couple of bookcases. Fractional units were used and the drawings were printed at a scale of 3/4 inch equals 1 foot. When printing any drawing at a scale of other than 1:1 or full, it is necessary to always remember to set a proper overall scale or dim scale and LTS or light scale. It doesn't matter whether plotting in model space or paper space, it is vital to properly set those two variables. If the variables of dim scale and light scale are not set correctly, you can have dimension text that prints too large or too small. You can also have hidden lines print as continuous lines. Tutorial 19. This video is about making the drawing of a simple bookcase in model space using fractions and AutoCAD's isometric commands, and to make the drawing ready to plot at a scale of 3/4 inch equals 1 foot. First, in dimension style, the units have to be modified from the decimal default to fractional. Also, it will be necessary to type the word units and change the dialog box to show fractional rather than decimal. Next, on the Tools menu, click on Drafting Settings and select the isometric snap. The isometric snap makes it possible to toggle the crosshairs using the F5 key. That key allows us to draw on different planes, as you will soon see. Now I'll move into a split screen to make the drawing. Toggle the F5 key to set the crosshairs to draw the top or plan view. With ortho on, pick a point on the screen and draw a line 54-1/4, or use the decimal equivalent of 54.25 if so desired. Move the mouse and type 22, move the mouse and type 54.25, and then move the mouse and type C to close. To draw the left side of the bookcase, we have to toggle the F5 key. Now draw a line from the intersection 30 down to 36 units, toggle again, enter 22, and move the mouse up to connect to the other intersection. Now, starting on the right side, draw a line downward 36 units, move the mouse to the left and connect to the left side. And break this last line in the middle somewhere. To show the thickness of the material, we'll offset the lines in front a distance of 0.75. After that, it's necessary to clean up the intersections using the FILLET command with a 0-degree radius. In order to save time, I'll complete the actual drawing by copying and pasting the shelf. Before dimensioning the drawing, we should change the dim scale variable to 16, because it's our intention to plot this drawing at 3/4 inch equals 1 foot. That means that 3 inches equals 4 feet, or 3 inches equals 48 inches. Therefore, 1 inch equals 16 inches, so the dim scale has to be changed to 16. In placing dimensions, you use the Align Dimension command. In addition to using the Align Dimension command, it's necessary to select from the Dimension menu the Oblique command, which helps to properly position the dimensions. The angle to be specified for the obliques is either 30 degrees or minus 30 degrees, as the case may require. Finally, when plotting this drawing in model space at a scale of 3/4 inch equals a foot, the company format has to be inserted at a size that is 16 times larger than the normal format drawing. On the other hand, if plotting this drawing in paper space, the viewport containing the drawing should be set to a scale of 3/4 inch equals 1 foot, and the company format is inserted at a scale of 1:1.
After examining my AutoCAD Blackboard page, if you have any questions, send me an email. Feel free to ask questions of any sort. I always like to hear from students. Thank you for watching.